In this tutorial, we will be writing a simple code to transmit and receive a character, and we'll also discuss about how the AVR generates its baud rate, or the frequency at which the serial communication works. And after that, I'll show you the Explore Embedded UART library, with which you can not just transmit and receive strings, but you could also transmit numbers like the printf statement does, in hexadecimal, in binary, even floating point numbers, and even binary numbers, which come in very handy when you are interfacing, or when you are debugging your circuits and you need to know what exactly is going on inside the controller. So let's just go ahead and first look at how the AVR generate its baud rate. So internally on the microcontroller, so this is inside the UART circuitry of the AVR. So what we have is a down counter or a prescaler, and it takes input from the the resistor, which we load a certain value. So this resistor, it's called the UBRR. So you have seen this resistor before when we were discussing it in the last video. And so this is basically a prescaler or a down counter. Okay, and then the input source for all of the frequency is the oscillator. And what it does is, since it's a down counter, if we load a value in this particular UBRR UBRR resistor, it starts counting down. Okay, and say we load a value 100 in the UBRR, it keeps decrementing with the oscillator frequency. So it runs on the oscillator frequency, so it decrements every so the time for every tick, or the time it spends doing down counting this, and this, let's say it is TP, and this time it's given by 1 divided by the oscillator frequency, F oscillator. And if we load the number 100, and let's call that as X, if we load X, the total time the prescaler would have spent is X divided by F oscillator, or the oscillator frequency. Now if I invert this, so it would be, so this frequency, let me call it as FP, it would be F oscillator divided by X. Now since it decrements from this value to 0, it does not decrement from this value to 1, it decrements from this value to 0. So actually the number of count it takes is the number we load plus 1. So let us call that X plus 1 instead of X. And so this is the frequency at which it counts, and usually the standard baud rates are 9600. It starts from say 2400, then we have 4800, 9600 is fairly commonly used. You should have also seen baud rate of 19200, then you have 115200, and it goes on till about 1 megabits per second. So that is this frequency I'm talking about. So now this frequency, since this runs at say 16 megahertz or 8 megahertz, and the value that you get here, it's still pretty large. So what we do after this is, what is done inside is, it is divided by 2, then it is divided by 4 again, and it is divided by 2 again. So we'll see what happens here. And then the last section where it is divided by 2 again, it could be bypassed, and you could get one of these two values as the baud rate. Now before we do that, so let's just complete this. So and the frequency, so this is the frequency that we get at this point. Now if I want the frequency at the last point, So that is our baud rate. So let me call that as FB. So this would be F oscillator divided by x plus 1 into, this is divided by 2 into 4 into 2, which is 16. So this is how you get the formula to calculate the baud rate. Now usually we know the baud rate, prior, like we need to communicate at 9600, so we already know this value. So what we really need to calculate is the x, so what value should we put in the UBR resistor in order to get this particular frequency. So if we solve for that, so x plus 1 becomes F oscillator divided by FB, and the baud rate we need, into 16, or x equals F oscillator divided by FB into 16 minus 1. Now let us do a quick example for the 9600 fairly common baud rate. So the value that we need to put here, yes, so we are running on a 16 megahertz crystal, and that is and we need a baud rate of 9600. So into 16 minus 1, and if I do that, the value is 103.16. So we cannot put a decimal value in a resistor, so we put the value 103. Now this one, 0.16, it generates a little error, but usually the communication is safe and we transmit data in a good condition. So this is the value if we need 103, 9600 as a baud rate on a board which has a 16 megahertz crystal. Now there is a ready-made table that you could look up in the data sheet which gives you the example baud rate setting for all the most of the crystal values. So let me show you that. Now if you look here, so this is the oscillator frequency, and then this is the baud rate, and this is what you need to put in the UBRR resistor. Now if I just scroll down and look at the 16 megahertz oscillator, and I hope it is there in this sheet. Yeah, so this is the 16 megahertz oscillator. Now for 9600, the value that you get is 103 as we have calculated, and if you do the error rate, it is about 0.2%, which is good. So you should just ensure that you do not work at error rates which are higher than 2 or 3%, so that you might miss a few characters. So 9600 looks decent here. Now let's go ahead and so you should also observe one more thing here. If UTX bit in one of the resistors, so let me just check which resistor it is, and if that bit is 1, the baud rate doubles. And if you look at our diagram, so let me just go back. So if I bypass the last divide by 2, so this is bypassed with the help of a multiplexer. So if so there's no space here. Okay, so let's see. So this depends if this particular line is selected, if the U2X bit is set. If U2X bit is equal to 1, then we directly get this frequency, and since it's not divided by 2, it is double of what we get. So if U2X bit is set to 1, then if you put the value of 103, so you get a different value altogether, and then the baud rate doubles. So if you put 103 as a value, and if you set U2X as 1, then you get double of what you initially thought. So if it is 9600, it becomes 9600 into 2, which is not a standard baud rate, but still it is useful in some cases when you want to double the baud rate. Now let us go ahead and look at the resistors once, and then we'll write a small code to transmit a single character. Now, so the first resistor is UCSR A, and if you remember, so this resistor, just for monitoring. So in order to know whether a bit is whether a character is transmitted or not. So RxE tells us when the transmission, the reception is complete. Similarly, TXE when the transmit is complete, and UDR when the data register is empty. So from this, we will be monitoring this UDR register to see if whatever we are given to controller, it has transmitted or not. So we will be just monitoring this and not be using any of this for this particular video. Now let us go ahead and look at the second register. And as discussed earlier, so this enables all the interrupts that we require. So these 3 bits enable the receive interrupt, transmit interrupt, and data entry interrupt, which we are not using. So what we need to do in this particular video is we need to turn on the receiver unit, the transmitter unit, and then even this bit we are not using, and since it's just 8-bit communication, we are not using the 9 bits here. So remember that the value of this, so we should set the RxEN and TXEN. So it should look something like this: UCS RB equals 1 shifted by RxEN. So this enables the receiver, or with 1 enable 1 shifted by TXEN, which enables the transmitter. Now, and we have said this before, so UCSRC, there are 2 bits here which define the data transmission, the each size of each character which is transmitted as 8 bits, and to do that we need to set these 2 bits as 1. And we also seen that in order to use this particular register, UR select bit should be 1. So when we write the code for this, it should look something like this. So we should turn on all the 3 bits, UR select. Although the default value is all 1, it is recommended to set them to ensure that you're doing the right thing. So this is 1 shifted by UCSZ1, and similarly 1 shifted by UCSZ0. Now and finally what we do is, this is the UBRR L register. So the value is just 103. If your value exceeds 103, or if your value exceeds 255, you can use the UBRRH, and you can use the 4 bits from UBRRH. So in total you have 12 bits for the total UBRR register. So our value is just 103, so we'll load it in UBRRL register. So this becomes 103 in decimal. So with this we can initialize the UART, and we'll write a small function to transmit a character, and in that function we'll monitor the UDRRE bit. So this bit tells us if a character is transmitted. So in the first little example, we'll transmit a character in C. So we do that by, now let us go ahead quickly and write the code to transmit 1 character repeatedly from the controller to the computer. So let us write the first function first here to initialize the UART. So it is better to write functions for all of this, because you will be using it quite a few times in your code. So this function just initializes the UART, and we have seen we need to do the following things. So we need to first set the register B and the C. So these are configuration registers, and this particular register here, UCSRB, we need to turn on the receiver and the transmitters. So UCSRB equals enable the receiver as well. Okay, so that's done, and even we need to configure the UCSR C register, and with this we just need to first select it. So, and that bit is URSEL. So this selects the register itself, and then we need So you'll find this, always you'll be using it in the 8 bits mode, wherein you'll send a character every time, and for that we need to set the bits UCS, Z1 and Z0. Z0 and so these are the configurations. So this thing here, it enables the UART, it enables both the transmitter and receiver. This here sets it to 8-bit mode. Next we need to load the baud rate into the UBRR register. So UBRRL, and since a value is just 103, it fits in the lower 8 bits, so we're using the UBRRL in this case. So this is loaded with 103, and this should initialize a 16 megahertz controller with a baud rate of 9600. In fact, you could write it in a much better way, wherein it accepts the baud rate as input, and then it does the calculation which we had discussed, and then it sets the baud rate to the desired one which you had passed. And we have written a good library which takes the baud rate as input and then does the calculation and initializes all of this, and I'll show you that in the next video. So let us go ahead and write a simple function again to transmit a character. So let's say this as UART and this, it takes a character as input, and that character, let's say it as data. Let's call that as data. Then what it does is, and we have seen that we need to monitor the UCSRA register and the UDRE bit. Let me show you that. So the UDRE bit here, it becomes 1 when this is empty, so it means that it has transmitted the previous character. So you need to wait till this is 1. So to do that, we just use the while thing, while loop, and then you wait here till it becomes 1. This and it with the UDRE bit. Okay, this is 1, this is 2, and this is 3. Okay, and once that is done, what we do is we'll put the data to the UDR register. So the UDR register is a buffer which puts the data into the buffer register, which is transmitted by the hardware unit. So these are two basic functions, so we'll use them in the main code and we'll transmit a character repeatedly. So to do that, it should be pretty simple. So first we need to initialize the UART. So we've already written a function for that, and then UART and we'll transmit ASCII value of letter A. So this will be done all the time, and we should see if we set program like terminal to 9600, we should repeatedly get letter A from the controller to the computer. Alright, so there are a few tips that I would like to give you before I'll go ahead and show you the output of the previous program. So if I connect this board, okay, so this board has a USB to UART converter, this particular small chip here, which converts data from UART to USB. So if you're using one of such converters, ensure that as you can see here, it detects in the device manager and you have installed the driver for this. And one more thing that you could try and do is you could short the RX and TX pins of the USB to your chip, and then if you type something in the hyperterminal, it echoes back. That ensures that this chip is right and everything is set up properly. So let me just go ahead and show you the output of the previous program. So I already transferred the code, and so let me just show you that. So I have this programmer called program called the terminal, on which we get the data. Now the port that is detected here, it's COM3. So I'll connect this on COM3, and the baud rate is 9600. So as soon as I connect, I start receiving the data from the USB to UART chip or the controller. So say if I reset the board now, it stops and it should start again. So this is how we transmit a single character. In the next video, we will see how we can go ahead and use the library and do all sort of things with the UART. Thank you for watching.